Hi everyone, my name is Noam Schiller.
And I'm Barak Katzir.
And we'll be talking to you today about our work in induced superconductivity and fractional quantum Hall edges in the presence of dissipation.
Before telling you about the details of the work, we'd like to mention our collaborators. From the Weizmann Institute, we have Professors Erez Berg, Adi Stern, and Yuval Oreg. And from the Technion, Professor Netanel Nidner. So the motivation for our work started with looking at the process of Andreev reflection in quantum Hall edge states. These processes have been suggested as key features of systems capable of harboring parafermion zero modes, which in turn have been suggested as building blocks for topological quantum computers. So we won't go into the theory of these, but here are some reference and also three experimental works pursuing this approach. Our work is motivated by the results of this particular work by Gul et al. From Harvard. In this experimental work, they looked at quantum Hall edge states in graphene coupled to a superconducting finger. You can see pictures here to the right. And in their work, they showed that they, well, firstly, they successfully coupled the superconducting finger to the edge states. They see this by measuring negative resistance. And the results show two key features. The first is that this negative resistance is small, but finite. So this is a proof that there is Andreev reflection in their system. And the second key feature is that the signature of the small negative resistance is qualitatively different when comparing the integer and the fractional cases. This is shown in the figure to the right, but we'll explain the difference a little bit later in this talk. So trying to explain these two key features is what we set up to do. And the key ingredient we thought would be dissipation. Such dissipation may possibly arise in the experimental setup due to vortices forming in the superconducting finger due to it being subjected to strong magnetic fields. This dissipation explains pretty naturally the small negative resistance, but not only that, as we will show, it also explains the difference between the integer and fractional cases. We did this by modeling a dissipative edge model coupled to a superconducting finger. And then, yeah, so our model looks as follows. We have a chiral edge state, either integer or fractional, going around a superconducting finger. And in the finger region, we have a continuum of subgap states. And these mimic the supposed vortices that form the experimental setup. And we place a bias V and measure the current downstream I. That way we can extract the conductance in this system. Now let's look at the different processes that can happen in our model, and then this will give you a rough picture of what exactly our model looks like. So first thing that can happen, a quasi-particle or an electron can traverse along the edge unhindered by any superconductivity or dissipation. Now, another process that we allow in our model is Andreev reflection, where an electron is cross-Andreev reflected to a hole that continues downstream. This process contributes to a negative conductance. Another process that can happen is backscattering, where an electron hops from an edge on one side of the finger to an edge on the other side of the finger. This process contributes to a positive conductance. And another process that we have is the dissipative process, where an electron hops to the subgap states and leaves the edge system. So charge is lost, and the more prominent this process is, the more the conductance will tend to zero. Already we can note a key difference between the integer and fractional cases, where in the fractional case, for the all of these processes involve unit charge. So for any of these processes to occur, you need multiple fractional quasi-particles to participate coherently, as you can see in the animation.
So now that we've described our model, let's go a little bit into our results. Here we have two plots. On the right, we have the same plot that we had earlier from the experimental work. And on the left, we have the plot of our results, where we plot the conductance at the exiting reservoir at zero bias as a function of temperature. And here we have two curves that we can see are pretty qualitatively different. In purple, we have the curve describing the conductance of the integer states. And we see that at low energies, this pretty much plateaus as a function of temperature and reaches a constant but negative value. Comparing to the experimental work, this is rather similar to the curve we see in green or in yellow of the integer quantum Hall states. Comparatively, the orange curve describing the fractional states looks very different. As we decrease temperature, the conductance becomes monotonously lower, or conversely, we have a more negative conductance, which corresponds to more Andreev reflection. So again, it seems as we lower the temperature, we have more and more Andreev reflection. Here, it's worthwhile to point out a subtle but important difference between our plot and the experimental plot. We plot a conductance, which goes from a value of minus sigma xy to plus sigma xy, whereas in the experiment, they plot the probability of a particle to undergo cross-Andreev reflection. So a value of minus 100% on the right plot corresponds to -1 in the left plot. So having said that, let's talk a little bit more in detail as to what these results mean. For the non-interacting integer states, our model is actually exactly solvable. Even when we add our three processes into the Hamiltonian, it's still quadratic, and we can just solve it and find the conductance of the system. In the case where we have no dissipation at all, this conductance will be exactly quantized. And we'll take one of two possible values, either plus e squared over h for the case where backscattering dominates Andreev reflection, which would correspond to a topologically trivial phase, or in the case where Andreev reflection dominates, we have a negative conductance of minus e squared over h, and this will correspond to a topological phase with the Majorana zero mode at the interface of the superconductor. Again, we emphasize here the point that a negative conductance corresponds to more Andreev reflection than backscattering, such that the minus e squared over h value is the topological phase. If we do add dissipation into our system, then we can still get this negative conductance that corresponds to more Andreev reflection than backscattering. However, this will no longer be quantized. And this is because the dissipation corresponds to some current loss in the system and effectively ruins the topological phase along the edge. This is qualitatively different than what we see in the fractional states. In the fractional case, we have our three processes, and the conductance is dominated by the process amongst the three that is least irrelevant in the RG sense. So even though all three processes can be irrelevant at the same time, what we care about is which is least irrelevant or most relevant. In the case that we plot, here we carry over the plot from the previous slide in the upper right corner. The case that we plot is dominated by Andreev reflection. And in the case where Andreev reflection dominates, we indeed see more and more Andreev reflection or more and more negative conductance as the temperature drops. The parameter that governs which of the three processes is least irrelevant is the interaction between the fractional quasi-particles on the edge, which in one dimensions we typically characterize using the Luttinger parameter k, which takes a value of 1 for no interactions positive, larger than 1 for attractive interaction. So here we have a phase diagram of our system for larger and larger or more and more attractive interactions. At k equals 1, starting from the non-interacting limit, we have a trivial phase with no cross-interactive reflection at all. And as the interactions grow stronger and stronger and more attractive, then we have 2 sort of transitions. In the first, we have the stage where Andreev reflection becomes less irrelevant than the dissipation. At this point, we're still in the trivial phase, but we now see a finite amount of cross-Andreev reflection. As the interactions grow stronger and stronger, we arrive at a second transition, which is the point where the Andreev reflection becomes relevant in its own right. At this point, we obviously still have cross-Andreev reflection, but we also cross over from the trivial phase to the topological phase with a parafermion zero mode living along the interface. It's interesting to note that unlike in the integer case, in the fractional case, this topological phase withstands the presence of dissipation because the dissipation is irrelevant. So to summarize, we study a system with dissipation in quantum Hall superconductor hybrid systems. With this dissipation, we believe coming practically from subgap states living in vortex cores. In the integer quantum Hall states, this dissipation impedes the topological phase and leads to a non-quantized conductance, although we can still have a negative conductance if there is more Andreev reflection than backscattering. In the fractional case, this is very different. Because the dissipation is irrelevant, we have less current lost than in the integer case. And this we can explain to ourselves rather intuitively due to the picture we saw earlier, where in order to tunnel to the in vortex core states, multiple quasi-particles have to undergo a process and not just a single electron. In the case where we're dominated by Andreev reflection, we get more Andreev reflection as the temperature decreases. And in particular, the topological phase for a relevant Andreev process can persist even though we have dissipation, as long as the Andreev process is relevant. Thank you very much for watching.
Thanks.